take away from the end time. That you can stay for 3 hours if you want. The only rule we have is after an hour, people can leave without being rude.
Makes sense.
He's in the city today, but he'll be here tomorrow to talk to me.
Sayan will be here tomorrow,
Yeah. Okay. Thanks everyone for coming. It's a pleasure to have Sayan Das visiting us from UChicago today. He's going to talk about the geometry of directed polymers.
Thank you, Evita, for the introduction, and thanks to the organizer for inviting me. So is the sound okay? Okay. Okay. Yeah, so as Evita mentioned, today I will be talking about geometry of directed polymers. And here are some keywords that I have written here. My goal is to, at the end of the talk, hopefully you will have some understanding of these keywords as well as some appreciation of these keywords. Okay, that's my goal. Okay, so let me begin with a very simple question. Suppose you want to go from point A to point B. What is the best possible, and there are various ways to go from point A to point B. What is the best possible path you can choose from going to point A to point B? And I would like to give you a probabilistic way to answer this question. Well, if you have no information, then one way to answer this question is to model your paths in a very simplistic manner. One way to model all such paths is to just consider random walk paths. Maybe your point is origin 0, 0 and the point is in 0, the other point B. And by random walk paths, these are just paths which are slope 1 or minus 1. At each, so you can think of this as your time axis, this is as your x-axis. At each step you take either +1 or -1 step. And in this way you create a bunch of many paths, in particular n choose some combinatorial calculation, n choose n over too many paths, and you want to choose the best possible path. Well, in this particular scenario you have no extra information. The Euclidean length of all of these paths are exactly same. So the best possible thing you can do with given this information is, well, you're gonna choose any path uniformly at random. You shouldn't really bias any such path, right? So you're gonna put a uniform probability distribution. So this is what we call as the random walk model. Going from point A to point B, there are this many paths, you choose one of them as random. This is the random walk model. So this is one extreme where you don't have any information about these paths, but there is other extreme. Usually real life scenario is not like that. You are certain points, you allow some bias to certain paths, right? Certain paths are much more favorable than the others. Maybe there is some reward associated with it. So we can try to model that scenario as well. Maybe on each of the vertices there is some reward, like omega ij. And the idea is whenever you visit that vertex, you get a reward of omega ij. So for example, if you visit this black path, you will take care of this red vertices. You will get each reward as you visit those red vertex. And the reward of this path will be the sum of all the rewards of those red vertices. So that is like the reward of the path. Okay? And then if your goal is to just maximize your reward, then basically you're gonna choose the path which has the maximal reward. So now it is no longer a probability question, it is a completely deterministic question. You just choose the one path which maximizes your reward. It's really an optimization problem. The probability comes here because you don't have any idea about this reward weights, which we call as environment. Usually in probability theory we take this environment or reward to be just IID collection of random variable, independent and identically distributed. Then this reward function becomes a random object because the omega is our IID, and this model has been well studied. This is called the last passage percolation problem, where the rewards are IID, and once you know the reward, once you know the random environment, your path is, your objective is entirely deterministic. So this is the one extreme where everything is deterministic given the environment. What this directed polymer that I would like to talk about today is something that interpolates between random walk and this last passage percolation problem. Okay? So what is this directed polymer? So directed polymer, as we talk about this random walk paths, directed polymer is a measure on this random walk paths. You have this random environment, which is still an IID collection of environment, but now you're not going to pick the best possible path. You will pick the path with certain probability. So given this random environment, you're going to associate a measure on this paths, which is proportional to the exponent of beta times this reward function, times the sum of path of the rewards. So idea of the measure is now you are still playing the random walk game. It's not deterministic function of the environment. You are now giving more bias to those paths which have higher reward. That's the idea of the measure. So this is bit complicated because now you have two layers of randomness. First is the random environment. Omegas are completely IID, random environment. And given this random environment, you still don't know which path you're going to choose. You're going to choose it according to this polymer measure. So that is the second layer of randomness. Okay? So this is a model that interpolates between random walk and last passage percolation model. And it's a two level of randomness. Is the model clear? Because this is really, this is one slide I hope everyone can understand. Okay.
So the only way x comes in is through the omegas?
This x? Oh, this is like the end point. So here 6, 0 is the one. So you can think of n being the number of steps, 6 steps, and x is the end point. Yeah, good question. Okay.
So is it more like the last passage when beta is really large or something?
We will come to it. Very good question. Okay. But usually when we talk about random walk, it's like we don't consider from point A to point B. It's like starting from a point and then you take plus minus one step. So actually there are two kind of polymers. One is you're going to go from a fixed point to a fixed point. So this is an example. This is the one which we call as the point-to-point polymer. But you might be also interested from starting from a point and taking n steps. That is we call point-to-line polymer. Just I want you to get familiarized with some of the jargons that we use. The theory won't really matter. Just there are two kinds of polymers. Okay.
But you could also consider the same problem with the weights fixed. You don't have to make the weights random, right?
Yeah. We will come to it. All very good questions.
Still probability on
Yes. Okay. So actually, where does this model come from? So it was not thought about by interpolation between random walk and last passage. This model actually comes from another important physics model, which is the two-dimensional Ising model. So I don't want to go into the details. It's a model which is taking care of magnetic spins plus and minus. If you consider certain boundary conditions, so these are like plus spins and negative spins, and then a phase boundary will emerge. And what physicists, Hughes and Henley were physicists, they were trying to come up with a model that can model this kind of phase boundaries. And it turns out that if you consider this kind of scenario where there is no island, then if you write down the partition function, the normalizing constant exactly looks like this directed polymer model. So this is what motivated Hughes and Henley to consider this model. And since then, this model has been not only considered in physics, but very heavily studied in math and physics, both literature, to the point that we have now books written on it. There are very exotic features that we see in this model that really that made the mathematician very interested in this model. And we're going to talk about some of the very interesting features. Okay. So what are the interesting features? So again, this is the model. So some statistical physics jargon. So we often call this beta as the inverse temperature parameter. So as we saw, it interpolates between random walk. So beta equals to 0 is the random walk, and beta equals to infinity, you get back the last passage percolation model. So beta equals to infinity is inverse temperature, so we call it the zero temperature model. So the last passage percolation is the zero temperature version of this model. And what happens in this kind of statistical physics model, two kinds of phases emerge. One, so you might suspect, as some of you said, when beta is small, the model should roughly look like random walk. So indeed, there should be some kind of beta critical below which the model, if you just zoom out, it just looks like a random walk, which we call the high temperature phase. Where by random walk, I mean, as you know, all the diffusivity of random walk is like root n. So we expect to see that when we zoom out, it's just like a random walk. However, there should be another phase, the low temperature phase, where beta is bigger than beta critical. And the idea is here the macroscopic features of the model is very, very different. It no longer looks like a random walk. I'm going to tell you what it exactly looks like in a moment. But the punchline of this slide is, for directed polymer, the phase transition happens exactly at beta critical equals to 0. So in other words, you have random walk, but for every positive beta, you see something which is completely different from random walk. You see a very different beast. So there is no, the phase transition is trivial here for dimension 1. Okay? So the question is, what is the low temperature phase? What we expect to see? Now I have to be a little bit careful. This model is complicated because there are 2 layers of randomness. So when we have 2 layers of randomness, sometimes we are interested in the annealed behavior. So annealed behavior is something where you resample both the environment as well as the random walk. You are resampling both. Okay? So both the environment, both the randomness you are resampling. So the punchline here is that when you resample both the environments, you are supposed to see that the polymer is deviating much larger than random walk. It is like n to the power 2/3. So the random walk behavior, it is often called diffusive behavior. Since here we expect this to be n to the power 2/3, this is called super diffusive behavior. This is what we expect. This is not quite proven. Okay? And usually to address this kind of question, like a 2-layer of randomness, is very hard to address this kind of 2-layer of randomness question. So how can we try to achieve this n to the power 2/3 if we want to prove? One way to achieve this n to the power 2/3 is to look at what we call as the free energy. Free energy is the log of the partition function. What happens in this kind of statistical physics model, you can understand a lot of the behavior of the model by just looking at just the normalizing constant. This is a very general philosophy. If you can understand the normalizing function very well, you can say a lot about the underlying path properties of the model. So one way to address this question is to look at the free energy. If we can understand the free energy well, we can understand it. So there is a very important conjecture, which is the strong universality conjecture. So if you consider the free energy process, it should have some kind of law of large numbers. Once you subtract it, the fluctuations are of the order n to the power 1/3, and if you want to scale it up, you will take n to the power 2/3. Then the conjecture is it should go to a universal scaling limit, which we call the Airy-2 process. The names are not really important here. What I want to kind of make the analogy is with the random walk. So in random walk, what happens is this fact that in the random walk, when you have a mean zero variance random walk, if you scale it by n to the power half, then the random walk goes to the Brownian motion. So Brownian motion is the scaling limit of the random walk. Here it is saying that if you consider the free energy, it goes to a scaling limit which we call the Airy-2 process. And while the Brownian motion has Gaussian behavior, normal behavior, the Airy-2 process does not have Gaussian behavior. Its marginals are given by something called Tracy-Widom. So
What is the D above the arrow?
This one?
No, above the arrows.
Maybe in distribution.
Oh, in distribution.
Oh,
Yeah. In distribution sense. Right. So Tracy-Widom distribution is something that arises in random matrix theory. If you look at a random matrix with Gaussian entries and make it symmetrized, and if you consider the largest eigenvalue, those distributions are given by Tracy-Widom. Okay? The point here is this exponent 1/3 and 2/3, particularly this exponent 2/3. So once you can prove this kind of result, it will actually tell you that the end point of the point to line polymer, it is fluctuating of the order n to the power 2/3. So this n to the power 2/3 somehow captures this n to the power 2/3. It's just a matter of writing it down. So this is how if you can understand the free energy conjecture, you can address this kind of questions. Okay. And this is a very long-standing open conjecture. We are very far from proving this conjecture. This is the scaling limit of the free energy. And this 1/3 and 2/3, this is actually nothing special about the directed polymer. In fact, there are like a huge, not a huge, but a very substantial class of models, which we call KPZ models. I will talk about the acronym KPZ a little bit later. So there are various models. Some of them are listed here. The macroscopic descriptions of the models are very, very different. Such as we already talked about directed polymer. You can think about the largest eigenvalue of a random matrix. The descriptions are very, very different. However, if we zoom out, we see that similar kind of exponent, 1/3, 2/3, this Tracy-Widom, AD2 process, they all appear. So this has its own universality class. We call it the KPZ universality class. And much of this is still conjecture. The directed polymers, the strong universality is still conjecture. But through simulations and through various computations, it is believed all of this model and various other models belongs to this universality class. So the features of this universality class is this 1/3, 2/3 exponent and some appearance of this Tracy-Widom and AD2 process. So this is not a feature of intrinsic to the directed polymer. It is expected to be there in lots of other models. Okay. Okay. So this is the annealed behavior. But there is something very intrinsic to the polymer, which is not on the other models, is the quenched behavior. So what is quenched? As he was saying, what about if we take omega to be fixed? If we assume that environment is fixed and we are sampling the random walk again and again. This is an actual simulation. You can see the simulation is very different, right? I am fixing the environment and I am sampling my paths again and again. What we see here is some sort of emergence of a favorite path, right? As if there is a favorite path and you are trying to kind of concentrate around those favorite paths. In statistical physics terminology, we call it a phenomena of localization. You are not really that spread out, like n to the power 2/3. You are actually now kind of enforced in a very small corridor around a favorite path. And there is a very important conjecture around in this quenched behavior, which is the favorite region conjecture. It says that almost every environment, you are supposed to get a corridor like this, and the length of the corridor should be always order 1. No matter how long is your polymer, the length of the corridor is always order 1. This is a feature that is very interesting, that we don't see in the other kinds of KPZ model. This is feature very intrinsic to the polymer. Okay? This is the quenched behavior, where we expect to see localization. Okay? Okay, to summarize, there is this directed polymer model. It interpolates between random walk and last passage. It has 2 layers of randomness. We can talk about what happens when we resample both the randomness. We see this kind of universal feature, 1/3, 2/3 Tracy-Widom AD2 process. Another feature, we can talk about what happens if we fix the environment. Then we see some kind of localization features. And there is this famous conjecture, favorite region conjecture, that we talk about.
You also study the continuum limit of this kind?
Yeah.
And do you still expect this single?
I will talk about it. Yeah. So this is a discrete model, but is there a continuous model? So before going to what we know about these 2 conjectures, let me talk about a continuous model. So the idea of continuous model is, okay, discrete model is like you have a discrete random walk and the discrete random walk is influenced by a random environment. Can I create a continuous random walk? By continuous random walk, it's just the Brownian motion. Can I come up with a model which is like a Brownian motion, which is influenced by a continuous random environment? And it turns out that if you want to figure out that process, what you can do, as we saw, there is no phase transition in directed polymer. You can still take beta to be going to 0. Then you can still take a limit such that the diffusiveness of the random walk as well as the effect of the environment both survive non-trivially. And this is something Albert Khanin and Questel did. They considered beta to be this particular setting. This exponent is important. And they saw that this partition function then converges to a non-trivial object, and the polymer itself converges to something we call the continuous polymer. So this was mathematically proven by Albert Khanin and Questel, but the physicists already knew what would be the continuous polymers, and they were already playing with the continuous polymers since 1990s. Okay. The interest in this model comes because these partition function have certain description coming from SPD. So if you look at the partition function of the continuum polymer model, this actually solves stochastic heat equation with multiplicative noise. This is a very important SPDE. And if you look at the free energy, which is the log of the partition, this also solves a very important SPDE, which is the KPZ equation. Okay. Now, I need to tell you a little bit about KPZ equation. This is because this is a very important model in our field. So what is this KPZ equation? So KPZ equation is a stochastic SPDE given by this. It was introduced by Kardar, Parisi and Zhang. So in our field, everything is called KPZ because of this Kardar, Parisi and Zhang. So KPZ stands for these three physicists. It was introduced about 40 years ago, and what they were trying to do, they were trying to model growing interfaces. So they were not interested in polymers at that moment. They were trying to model growing interfaces that has certain features, that has certain smoothing mechanism. So this Laplacian denotes that smoothing mechanism. That has certain slope dependent growth. So this second term denotes the slope dependent growth. And this third term, which is I call Xi, which is it's a space-time white noise, but those who are not familiar, you can just think of this is like a continuous random environment. And the third term denotes that the height is kind of driven by a continuous random environment. So based on these three postulates, they came up with this model. And this is supposed to be kind of the universal limit itself for various growing interfaces that has these three features. For example, this is like a Tetris model, which also kind of have this feature. This is like the snowfall model, where if you suppose snow is falling, unfortunately today is a very bright day, snow is falling on the windshield or something, you are supposed to see some kind of interface which resembles this sort of features. So all of these interfaces are supposed to be like KPZ. So this is an SPD. So this has garnered, this is actually a singular SPD. It's a bit difficult to make sense of this term because the space-time white noise is a bit rough. So that has attracted a lot of attention for SPD community. So there are various methods that have been went into in showing how to make sense of this KPZ equation. This equation is actually ill-posed. You cannot solve it in the usual manner. So for example, Martin Heidegger proposed this regularity structure theory to solve the KPZ equation, for which he owned the Fields method. Besides being an SPD of its own interest, as I just showed you, it is connected to the directed polymers. And in fact, it is connected to other kinds of processes as well, like exclusion processes, which Evita works on. So for this model, the KPZ equation is very interesting model to us. This is like the jewel of our KPZ university class. KPZ university class has so many models, some of them are conjectured, but this is kind of like the jewel in that class. Okay? So just a side note. But today we're not going to talk about the SPD aspects of this model. For us, it will be just the free energy of the continuous polymer. So think of KPZ equation is we have this continuous polymer, Brownian motion going through random environment, and the free energy of that polymer is KPZ equation. That's it. Okay? Okay. So hopefully the theory is clear. There are discrete polymer, there is a continuous polymer, and there is this entire theory. Now I have to tell you a little bit about what we know about these conjectures. Any questions? Okay. What we know about these conjectures. So the discrete polymers, we are very far from proving this strong universality conjecture. So why is it called universality? Because the random environment can be anything. So the only environment where we can have made progress so far is a very particular environment where we assume that the environment is coming from something called log gamma distribution, which is a kind of a standard distribution in undergrad probability theory. So what this Sepelinin, he made the breakthrough. He considered this very particular environment. What he saw that if we somehow change the boundary condition of your polymer, not consider the usual polymers, changing the boundary, then the model actually becomes stationary. It's stationary in the sense that the partition function satisfies some recurrence, and basically if you choose this weight, then that recurrence then it becomes a fixed point basically. And you may ask why log gamma is so special. It is because of an undergrad level probability fact that if you have x, y, z as independent gamma distribution, if you take this transformation, then the distribution of this transform random variables is exactly same as this. This is a very basic fact in undergrad level probability theory. Not a fact, but a very good, nice exercise. And it turns out that these transformations are important because these are the exact transformation that appears in the partition function recurrence. I'm not showing you the partition function recurrence. It takes a time, a little bit to write down and to see, but believe me, these are the same things that appear there, similar things. So that's what kind of motivated Timo to come up with this model. And this observation was very useful because this led Timo to derive the 1/3 and 2/3 exponent. So what do I mean by 1/3 and 2/3 exponent? We already saw it. So Timo just analyzed the free energy function. He showed that indeed up to tail estimates is like 1/3 and 2/3 exponent are the right exponent. He didn't have any precise fluctuation. He didn't have Tracy-Widom and Airy-2 process, but still he has the correct exponents. So this was the breakthrough. Okay. By the way, I am leaving lot of literature, not even stating it. The last passage versions of this model have been very, very well studied. And I'm not giving you any reference to those models because otherwise this talk will be all about talking about reference. I'm just talking about what are the stuff that has been done solely for the directed polymers. And directed polymers is a bit harder than the last passage percolation model. So the results are a bit scarce. So what about the precise fluctuation? What about those Airy-2 process and Tracy-Widom? For probabilists, it's very important to get those scaling limit kind of results. For those results, there needed to be a very different kind of methods, which we now call as the integrable methods. There is vast literature on LPP, so I'm just stating the directed polymer stuff. So what is the idea of the integrable methods? As it turns out that this log gamma polymer and the continuous polymer, they have certain very important structure, very special structure, beyond those gamma distribution identities. And these special structures comes from other branches of mathematics. So I have listed some keywords here: McDonnell polynomials, Whittaker function, RSK correspondence. I mean, those who know it may find it familiar in case someone knows it. But the point is, through those structures, we get very exact formulas for our models, log gamma polymer and continuous polymer. And then basically, to get those Airy-2 process and Tracy-Widom, it boils down to doing some hardcore analysis of those formulas. So there is no probability involved, it's just hardcore complex and real analysis. And this was kind of the crucial step in the early 2000s, and using those hardcore analysis, it was shown that Tracy-Widom fluctuation is indeed there for the log gamma polymer and the continuous polymer, for these two polymers. So Tracy-Widom fluctuation, the 1/3 exponent. These are the two kind of first papers, but there are other papers in this direction as well. Now there is this another exponent, which is this 2/3 exponent, which signifies how your polymer is super diffusive. That 2/3 exponent, or the scaling limit Airy-2 process, is a bit harder to get, which is not quite accessible solely through exact formulas. Then what happens, since last decade or so, people realize that those ugly looking integrable formulas, they have certain probabilistic meaning. They can be interpreted in a probabilistic way. one can still use probabilistic methods to analyze those ugly looking formulas. And this gave birth to this what I call as integral plus probabilistic methods. And these are some of the kind of names who have done like important works in these methods. And eventually we obtained the AD2 process convergence for these two polymers, log gamma and continuous polymers. So we have the AD2 process convergence, the scaling limit convergence just for these two polymers. That's it. So this is all we know about the annealed behavior of these two polymers. Just these two. Okay? Okay. So what about the quenched behavior? What we know about the quenched behavior? So for the localization aspects, so the localization literature is even more scarce. What happens is the stuff that has been done is only focused on point-to-line polymers, and you can only say about the end point of the point-to-line polymers. This is because there is some martingale structures in this point-to-line polymers. So that's why they can only say about the end point of the point-to-line polymers. And since this localization conjecture, the favorite region conjecture is so hard, there have been easier versions of this conjecture that people have tried to understand. So these are some of the strong localization, which is like existence of favorite sites. So strong localization is not really strong localization, it's like the weakest one among the three. Then the atomic localization is a little bit stronger. I won't be able to tell you what it is, but they were also well studied. And then the strongest one is the geometric localization, which was well studied by Saurav Chatterjee and his student Eric Betts. The geometric localization, what it says, what they were able to show, that for positive proportion of the environment, you do see this localization feature, where all sample paths stay within the order 1 window. This is the strongest thing that we know about localization. And these results, they don't really depend on continuous or log gamma polymer. They are like true for every polymer, whatever they proved. But
this is on quenched situation?
Yeah. Whenever I say localization, it's about the quenched one. But I want to remind you that the favorite region conjecture actually says something stronger. It's not about positive proportion of environment. It's about almost every environment we expect to see this favorite path appearing. So this is not really attained by this set of authors. The only result in this direction that we know is the stationary log gamma polymer, which Timo considered, where they were able to show indeed for the end point of the point-to-line polymer, they stay within an order 1 window. So basically, this log gamma polymer with some stationary kind of boundary condition. What happens in this stationary model is, since it's a fixed point, there is no polymer work. If you want to study the endpoint, it essentially becomes a random walk model, and you are studying some random walk behavior of this model. So it essentially boils down to the analysis of a random walk in case of stationary model. Okay, so this is, before our work, this is all we know, okay, not all, but most of the important works that we know about the quenched behavior.
So your favorite depends on the environment?
Yeah, the favorite path will be a deterministic function of the environment, and then the idea is that all your sample paths should concentrate around this favorite path within an order 1 window. Okay. So then the question that I was interested in is there have been so much activities going on using this integral formulas and probabilistic methods to address this kind of annealed question. Why can't we use those methods to address this quenched question? We know so much about continuous polymer and log gamma polymer. Why can't we answer those questions, localization kind of questions, using those methods? So this is something I did with my academic twin, who is no longer in academia right now. For point-to-point continuous polymer, so this is continuous polymer, which this is hand-drawn, we show that if we look at the midpoint of the path, it indeed stays within order 1 window around the favorite point. So if you fix your environment, if you sample your path again and again, look at the midpoint, it will all stay within an order 1 window. There is nothing special with the midpoint. I'm just stating it for easier. You can take any point actually. So if you take any point around here, it will always stay within order 1 window. And we have an explicit description of this order 1 window if you are interested in the length or if you are interested in something. We have an explicit description, but it is a bit complicated, so I didn't write it in the slides. So this is the first proof of this kind of favorite region conjecture for any kind of point-to-point polymers, but this is only for the continuous polymer where we have a lot of activities. And as I said, the main kind of contribution is these kind of integrable tools that were used in the annealed situation. How can we use those tools to extract this kind of localization behavior? Okay. Any questions about this? Yeah.
Is the favorite point something explicit, or is it?
Yeah. So this, I'm saying it around the favorite point. So the favorite point also has an explicit description. Yeah.
So is it deterministic?
It's a deterministic function of the environment. It is always a deterministic function of the environment. But if you, it won't be like a super, it will be a function of the environment, not like that kind of deterministic. Yeah. So we have an explicit description of the favorite point. We have an explicit description of this length of the corridor, the whatever you want. We have very, very explicit description.
Does it matter for these things that the boundary conditions are fixed on both sides for these paths, or is that just an accident?
Oh, so this is point-to-point polymer, where you go from one point to the another. Doesn't matter which point you pick, doesn't matter. You can also consider point-to-line polymer. We have similar results for that as well. Yeah. Okay. So this is about the quenched result. The annealed one, I have already told you that there has been a lot of activities for the free energy one. We know a lot of things about the free energy. But still we were interested in what about the paths of the polymer itself. Given the free energy contribution, can we say about the paths of the polymer? Indeed, if instead of free energy, if you are interested in the paths of the polymer, so now you are sampling your environment as well as your polymer paths again and again. Okay, by the way, some drawings are hand drawn, hopefully you can realize, and some drawings are actually by simulation. So this is a hand drawn picture. So I am here, suppose I am simulating the environment as well as my paths. And then indeed, if you consider the annealed law, if you scale it by n to the power 2/3, you are supposed to see an universal process. So this is different from the free energy. Free energy only talks about the partition function. This is actually giving you a scaling limit of the paths. And this has a description, geodesics of the directed landscape. Don't worry so much, it is something. And here, essentially, the hard work was already done in the free energy setup. We were able to convert those hard results about the free energy to polymer paths. Okay. So these two kind of paper together gives us a very complete picture what happens to the annealed and the quenched behavior for the continuous polymers. Okay. And there is nothing special with the continuous polymer. We can still utilize those tools to prove it for the log gamma polymer as well. I mean, it requires some work, but I don't think there is any kind of intellectual new thing that needs to be explored here. So similar things one should be able to show for the log gamma polymer as well. Okay. So let me describe some of the works that I have been thinking about. Of course, this only proves things about only two polymers. There is still long-standing open question about what about the other polymers. And this localization aspect, as you just saw, I can prove it for the midpoint. I can prove it for any point. But what this localization truly says is there should be an entire corridor. Entire corridor where the paths is always staying through the corridor. It's like a pathwise localization. So this is the next big problem, to actually show that there is a pathwise localization for these two polymers. And again, these two papers by Saurav Chatterjee and his student Bates, they show pathwise localization, but again for positive environment, so for positive proportion of environment. It's not like almost surely for all environment. So this is some of the localization aspect that we hope to study in the future. And another kind of questions that I have been interested in is understanding the large deviation problem for these KPZ models. The large deviation problems is basically understanding the rare event of those models. Suppose the free energy is much larger than what you expect, much larger than the law of large numbers. So those kind of questions falls under the large division. It's a rare event object. One can ask what happens to those polymer paths when you are in the rare event. So suppose your free energy is high, what can you say about the paths? What happened to those paths? So this is something that I am also currently thinking about. Okay, so this is the story of full space polymers, these two polymers. So now let me talk about little bit about a new kind of a variant of the full space polymer, which we call as the half space polymer, which is also very interesting. Okay, so now I am down to my last line, half space polymer. So what is half space polymer? In half space polymer, we are essentially still looking at the polymer measure, but my environment is now changed. I have changed the environment in the following way. I am assuming that everything above x-axis is coming from a common distribution, let's call the bulk distribution. But on the x-axis, it is coming from a different distribution that depends on certain boundary parameter alpha. And below the x-axis, there is nothing. There is no environment. You can assume that the environment is negative infinity. So the idea is now if you assume that the environment is negative infinity, you're not gonna touch the negative environment, you will always stay on the positive side. So now your paths, the possible paths are only on one side of your x-axis. It will touch or it will go up. So this is why we call it as the half space model. Same model, I have changed the environment. And the idea or the philosophy of this measure is that I am still considering paths. The red one still denotes my random environment, but the interpretation of the blue one is like this x-axis is like a wall, and the blue one signifies how much the polymer is attracted to that blue wall. If your blue weights are smaller, then the polymer is repulsed away from the wall. If your blue weights are larger, then the polymer is attracted towards the wall. And this is a very physical model that models weighting phenomena. So think of this alpha parameter. As you increase the alpha, the interaction becomes weaker. So I can give you a very standard example. So polymer and the wall. So suppose you have a paint, okay, and the paint is on the wall. So under the usual temperature, the paint will stick to the wall, right? So wall is your wall here, and the paint is the polymer. Now suppose you increase the temperature of the wall. As you increase the temperature of the wall, the attraction will become weaker and weaker, and there will be a critical point. After that, the paint will fall from the wall. And we have seen this kind of phenomena in other physics model as well, particularly in case of magnetization. When you have a ferromagnetic object, and under usual temperature it have the magnetic property, but as you increase the temperature it loses the magnetic property, and there is a critical temperature, the Curie temperature, beyond which there is no magnetic property. So exactly same thing happens here as well. As you increase the temperature of the wall, it loses all the attractive property after a critical point, and it just falls off. So here are the real simulation of this polymer. If alpha is small, the polymer should stick to the wall, so this we call as the bound phase, and if alpha is large, the polymer should just repulse away from the wall. It should be something like a full space. And this model was actually relevant since the full space days as well, since 1985, and Kardar himself conjectured this kind of phase transition. So there is a non-trivial phase transition here which is not present in the full space polymer. We expect that there is a critical parameter below which the polymer looks like this within order 1 window, and above which it just behaves like a full space polymer, which is it should be like n to the power 1/3 and 2/3. This what Kardar called it as the deepening transition. It pins to the wall and deepens to the wall. Okay, this is the phase transition in the half space polymer model. And there is a similar phenomena in random matrix as well, and it is sort of related. I won't be able to tell you. There is this spiked random matrix model, where if you consider the random matrix like an IID random matrix, you can you can add a rank 1 parameter perturbation of this spike of this model. This is the spike random matrix model, and then you can ask like what is the feature of the largest eigenvalue. Here we also see a phase transition which we call the Bike-Benarus-Peche phase transition, BVP phase transition. This is actually very useful in statistics model. So these two models are very similar, the idea. So this is the half space. We see a non-trivial phase transition. Again, I will focus on only these two polymers, the continuous polymer and the log gamma polymer. And the boundary condition acts like this. So you're gonna choose a different kind of weights in the discrete polymer. And in case of half space KPZ equation, it boils down to choosing a boundary condition for your SPD. It is a Neumann boundary condition. And this alpha acts like the boundary weight. And this alpha is so chosen that the deepening transition happens exactly at 0. This comes due to some calculation. So what we expect is if alpha is less than 0, then we are in the bound phase, we are sticking to the diagonal. And if alpha is bigger than 0, we are in the unbound phase. We move away. Okay. So what we know about this model? So this model is, first of all, it's much richer, because it gives you an entire 1 parameter family depending on alpha. So it's much richer than the full space model. And we do have integrable methods here. We do have exact formulas. But actually these formulas are much harder to analyze. These are much more complicated formulas. All we know before our work is we do have fluctuations only when the endpoint is 0. So we do have this 1/3 exponent only at this endpoint. And part of the reason why half space is much harder is because there is a lack of translation invariance. In full space, as you can imagine, there is no boundary parameter. There is some sort of translation invariance in full space. And this translation invariance is actually very crucial to obtain from 1/3 exponent to the 2/3 exponent. It was a very crucial ingredient. But this translation invariance is completely absent in half space. We don't expect, because there is a boundary parameter sitting there in alpha, why there should be translation invariance. So that's why to address anything away from the boundary, like what are the fluctuation if this is not 0, or where is even the 2/3 exponent, what is the analog of my scaling limit, the area to process in half space, is much more harder. It requires some new strategies and idea in the half space. So for the past few years, I have been trying to develop some of the techniques and tools for this integrable probabilistic methods in the half space scenario. So my collaborators and I have been trying to develop this kind of settings. So I won't be able to tell you what kind of methods that we develop, but I would at least try to give you some of the results that we were able to show. Okay, so these are a couple of works that we did a few years ago. So we show that, okay, indeed if you look at the log gamma polymer, half space, then indeed we have the 1/3 and 2/3 fluctuation if we are in the unbound phase, and if we are in the bound phase, indeed it sticks to the diagonal. You can just, basically we prove that these two pictures are right. We show that if we are in the unbound phase, if you look at the end point, we can show that the end point fluctuates like n to the power 2/3, the annealed behavior. And if we are in the bound phase, then the end point is always within in the order 1 window. So these two papers proves the Kardar conjecture. So this is the first proof of the Kardar conjecture, and it also derives that indeed we have the 2/3 exponent when we are in the unbound phase. So we only do the free energy kind of computation. So we only look at the free energy, and one of the contribution of these two papers is we introduce this integrable plus probabilistic approach, which again I'm not going to be able to tell you in the half space. But we only have exponents here. We don't have any clue what is the scaling limit, what is the analog of the area to process. Because the discrete polymers are a little bit harder to analyze, it's always better to move to the continuous model. So then we move to the continuous model, which is the half space KPZ equation. Again, this is the free energy. There is a law of large number, and you see the 1/3 and 2/3 exponent. We show that if we are strictly in the unbound phase, it converges to a analog of the AD2 process. And if we are strict, like in the critical setting, alpha equals to 0, it converges to a different process. So these two are the analog of the AD2 process in the half space. We show it for the KPZ equation because it was easier to do with the KPZ equation. And there are two papers I have listed. So the first paper shows that these objects are tight, and we show that if there is a limit, how the limit should look like. And this next paper, which we are currently writing, we show that, okay, we already have some kind of characterization. We show that those characterization uniquely determines my object. So this second paper deals with the uniqueness. And this was inspired by my authors Agarwal and Huang, similar result for the full space. So this is how we achieve the scaling limit. So we show that indeed we have the KPZ equation setting, the continuous polymer setting, the scaling limit, we have a scaling limit. And as you can see, we don't address the alpha less than 0 case. We expect that the alpha less than 0, it will be just Brownian motion, because we are always within order 1, it should be just Brownian motion. Okay. And recently there have been exact formulas for these two limiting process by different authors, but our proof doesn't really rely on these two papers. We gave a not really exact formulas, but a probabilistic soft kind of argument to show that indeed there is a unique process in the scaling limit. Okay. Okay. Any questions?
What did you say what tightness means? Maybe I missed that. So these quantities are tight. What does that mean vaguely?
It says that how can I say? This is like a probabilistic. Right. What does tightness mean? It is some kind of precondition before. So tightness. So if you have a sequence of random variable, we say if it is tight, then what happens that if you consider any subsequence of that random variable, I know it converges to somewhere. Yeah. If it is a convergent subsequence, yeah. But different subsequence can converge to different things, right? So it doesn't really tell you whether my original sequence converges to the one single thing, right? So that's why we need another thing. We need to know there are some properties of the limit point. So all the limit points should satisfy some property. So this paper show that indeed it's tight, and if there is a limit point of the sequence, the limit point has certain properties. And the second paper shows that if I have those properties, the limit point is unique. So together it shows that we have the convergence. So tightness is a very easy concept in probability, but sometimes I fumble when I try to describe easy concepts. Anyway, so this is our contribution, and let me say some of the stuff I have been thinking right now. So this actually settles the question of showing convergence of free energy in case of the KPZ equation, half space KPZ equation. But of course, there are several questions you can ask about the half space KPZ equation. We left out the alpha less than 0 case. Of course, a very next question is to just show that Brownian motion convergence should be there. So this is something that should be doable. You can ask about various path properties, various bulk properties of the half space KPZ equation. So some of the properties I am currently studying with some of my collaborators. But half space KPZ equation is just one model in this half space universality class. All of those models that I have described before there is a half space analog of it, and once you have a scaling limit, then the next goal is to build up this universality class. So a long goal would be to build up this class to show that all of this half space model, at least those who are kind of easier to deal with, they all goes to this scaling limit process, right? So I am working with currently some on couple of papers in addressing some of the questions, like I'm working on some of the other models and showing that indeed they go to the same kind of objects. But of course you can talk about a lot of things. Okay, so that's it for today.
So since I have to run off, are there any other questions? Alex?
So I have a question regarding the two main conjectures that you stated. What happens on the unit two conjecture when you choose one of the value for which we record our emotion?
What happens to the 82
I mean, you described the process, and for some value of that process, for beta equals to 0, we got the random walk.
Yeah.
What happens in that? I mean, like, on what other cases is that conjecture? I'm guessing that.
Oh, the strong university conjecture?
Yeah.
That is only known for these two polymers. So only one environment, right? You mean this conjecture, right? This is, so why is it a university result? Because one believes that this should hold for all random environment. This should hold for all. So this is an IID collection. I haven't really told you what is the nature of the distribution. It is believed that as long as you take nice enough distribution in the sense that have exponential moments, let's say, I should still see 82 process. But right now, we only know it for only one such random environment, which is log gamma polymer. And since we know one such random environment, by virtue of it, we also know for continuous polymer.
Also, what does the favorite path conjecture say about potential scaling limits?
So in the favorite path conjecture, there is no scaling limit, right? Because everything is within order 1 window.
Oh yeah, but I mean, like, what can it say about potential scaling limits?
So what you can ask is, the favorite path, whether it goes to somewhere, right? This is one potential scaling limit we can ask about, where does the favorite path goes to. And the favorite path, I mean, the guess is very easy. Since the annealed law is going to some fixed path, this dt, you expect the favorite path to go to the same object. Yeah, so this is one conjecture you can think of.
So it's saying that instead of proving for the entire process, you can just like prove what it converges being the favorite path?
Yeah.
And earlier you didn't quite say what geodesic of directed landscape means. That's something you could say something about?
Right. So, yeah, what is this directed landscape? So basically, this is a last passage percolation terminology. So this last passage percolation model, you can essentially think of this as like a random metric model from point A to point B. This your maximal reward is like giving you a distance between point A to point B. And this random metric model, it converges to a universal scaling limit, which is like a random metric but in R2 on plane. This random metric, we call it as the directed landscape. So it's a random metric in R2. It's a directed landscape. So if you have a random metric, one can talk about geodesics and stuff like that. So that geodesic is that geodesic.
So your distance is how much weight you collect?
Yeah.
Do you have some back of the envelope understanding of this exponent 2/3 you could share for the scaling? How would you, maybe from KPZ?
So this 1/3 and 2/3 exponent, I mean, if you have 1/3, the 2/3 is actually always like 2 times this. This happens in one-dimensional case. And this 1/3, this comes from some calculation in, not in the directed polymer, but there are some other models where you can show. It's called the first passage percolation model, where you have some, if you assume something, then given half an hour, I can show you, okay, this kind of equation should come up. Yeah.
No other questions? Oh, you're sorry.
Can you mention about how KPZ is related with random surfaces? I saw that it was like in or random matrices. randometric model.
Yeah, this is the same model that I was speaking about. I mean, the last passage percolation model. You can think of this reward as your length, right? So that gives you a randometric model. Yeah. So instead of Euclidean distance between any 2 points, you can think of the distance between neighboring points in the lattice is like either 1 or 2. It's not always deterministically 1. It's either 1 or 2. That will give you a random metric, right? So that is the randometric model, and it is expected that this randometric model is within KPZ University class. But this 1 and 2 that I just described, we don't know. It's completely open.
Yeah, maybe you mentioned, but could you repeat what happens at the critical temperature as a transition? Are there any expectations?
For the full space or half space?
Let's say full space.
So in the full space, there is no critical temperature, right? At 0.
Okay. No, but for the positive temperature, you have the random walk. For the negative temperature, you have like this n to the power 1 over 3 kind of constraints, and which one is like the transition?
So for every positive beta, we are supposed to see this.
Yeah.
Yeah.
And what happens if beta is 0?
So if beta is 0, then it's just random walk because it's
Okay, then it is a random walk.
yeah. If beta is 0, it's a random walk. If for every positive beta, we are supposed to see something different, and for every negative beta, well, you can just take omega to be minus omega. So every non-trivial beta, we are supposed to see something quite different.
So there must be, you present this critical thing, and then you tell us that it doesn't exist, right? Did I understand correctly? You present the notion of a critical inverse temperature, and then you say that there isn't one.
Yeah, because
why would you ever talk about it if there isn't?
Because there is a non-trivial phase transition if you move to higher dimension. So if you think about the random walk, well, I'm only taking, one is my time axis, but the space axis is 1 dimension, right? So in 2 dimension, beta critical is still 0, but if you move to 3 dimension and higher, then you have a non-trivial phase transition. Then you actually have something non-trivial in high temperature phase.
And is that something people know very little about?
Yeah, so in general, if you want to ask what is going on in the high dimension, we know that there is a non-trivial phase transition if dimension is bigger than equals to 3. We have no idea what are even the exponents, even in dimension 2 or bigger than 1. Even we don't have any idea how to define KPZ equation in dimension bigger than equals to 3. Dimension bigger than equals to 3, it totally breaks down. And dimension equals to 2, people are just starting to have some idea how to define KPZ equation. It's still like in the beginning stages. Yeah.
Other questions? If not, then let's thank Sayan again.
Thank you.